this is Ms. Riggins with today's video in section 1.8 in limits. Please don't forget to watch, while you're watching the video, to take your notes and to work on your summary and any questions you may have, because it's your responsibility before the day ends to make sure that you submit your online WISC. So we'll be ready for class the next day. So let's talk about limits. Today we already know enough about limits because you use them in pre-calculus. The definition for a limit as x approaches some c value of f of x is it's going to be equal to some value L if the values of f of x approach L as x approaches c. And that's been a sufficient definition for pre-calculus. But now that we're in calculus, we need a better definition because the question arises, what is good enough to approach? That seems a very vague sense. And if we take a look at the function, here we have a function that we are wondering what happens as x approaches 0 to the function. And it looks like as x approaches 0 from both sides, it looks like the function is going to equal 0. So it seems like the limit as x approaches 0 of the function would be equal to 0. When in actuality, that's not how it is. Because as we zoom in closer and closer, what we see is that the function is actually getting close around 1 to 0 values, but it's actually oscillating back and forth, and there is no as x gets sufficiently close to 0, will f of x get sufficiently close to 0, or will x approach 0. So we need a better definition, and the better definition is going to involve not the word approaches, but it's going to involve the word close. So let's see what that is. Now, I know some of you may be saying, well, what's the difference between approaches and close? Well, because if you look at this definition, it says that the limit of f of x as x approaches c will be the number L if that f of x is as close to L as we want whenever x is sufficiently close to c, but it doesn't have to equal c. And that's important to note, that instead of just approaches, we say f of x is going to be as close as we want to L. And the question is, how do we determine that f of x is as close as we want to L? We'll pick some very small number. We're going to put x and L are going to be no more. We want it to be such that f of x and L are no more than epsilon away from each other. That's close. That's as close as we want because we are picking any number epsilon greater than 0. And we're saying that f of x and L are going to be no more than epsilon away from each other. Well, for every epsilon that we pick, then there's another number, delta, that will guarantee, if it really is f of x really approaches L, that delta exists such that x and c are no more than delta away from each other. And if that's the case, then you can say no matter what epsilon we pick, there's always going to be a delta such that x and c are no more than delta away from each other, means that f of x and L are no more than epsilon away from each other. And if that's the case, then the limit x approaches c of f of x is going to be L. And now this gives us a definition we call the epsilon delta proof, because it quantifies exactly what it means to be as close as we want whenever x is sufficiently close. So this says the definition of a limit is such that for every epsilon that we pick, no matter how, as long as epsilon is greater than 0, that we will always be able to find a delta that's also greater than 0, such that if x and c are within delta of each other, and x doesn't have to equal c, then f of x and L are always going to be no more than epsilon away from each other. So now we have a definition for what it means to approach each other, and that definition is quantifiable because it involves any value epsilon that we pick, where we find a delta that will also be where x and c are delta within each other. And now that's a more formal quantifiable definition of limit. So now let's take a look at how do we find that delta if we pick any epsilon. And actually, we're not going to have a chance to take a look at that because I don't want this video to be long. But on example 3, on page 60 in 1.8, it does give a good example of finding a delta whenever you pick any epsilon. Also on page 60, it talks about some properties of limits. And it's pretty much not difficult properties to understand. It's pretty much very linear, because it seems like we have the product property, we have the addition property, we have the multiplication property, and things of that sort, and division property. But these to know, so make sure you take note of these properties. But I want to talk about two situations. One situation with limits is if the limit does not exist, and we know that there are situations where the limit will not exist. If we go back to this problem right here, oops, not that problem, this problem, we see that the limit does not exist. Oops, sorry. There is no number, no matter what epsilon we pick, there will be no delta such that as x and c get sufficiently close, that f of x and 0 will be sufficiently close because it seems to be oscillating at this point. So there's certain epsilons we can pick where it will work, but not any epsilon greater than 0. So if the limit does not exist, we just say D and E. It does not exist. And in your book, they do have some good examples on page 62 of limits that do not exist. So the second situation is what happens as x approaches infinity? What if c is not some real, some definable number? What if c is infinity? How do we define the limit to? Well, in this case, the close to a number L as we want means that as long as x gets large enough, because it's never going to be with delta within infinity, because we don't know what infinity is. But as long as we get x sufficiently large, which means, 1,000, 100,000, 200 million, whatever, the f of x will be approaching L, then that is sufficient for it to be a limit as x approaches infinity, or in vice versa for negative infinity. Okay? All right, so we're almost there, almost done. The next thing and the last thing we want to talk about is the definition of continuity. And we've been using continuity, and we've kind of been using it with the idea of a limit, but now we're going to more formally define it. So f is continuous at a point x equals c if f is, number one, defined at that point, and if the limit as x approaches c of f of x is f of c. So now, before we were talking about continuous functions and continuous on an interval, now we're talking about continuous at a point. And there are two requirements for a function to be continuous at a point. It must first of all be defined at that point, where x is c, and then the limit as x approaches c of f of x should also equal f of c, in other words. Okay? So in other words, f of x is as close as we want to f of c, provided x is close enough to c. And we can use epsilon delta as well to prove that. Now, the function is continuous on an interval if it is continuous at every point on the interval. So if we can prove that this will hold for every point in the interval, then we can say that the function is continuous on an interval. So now we have another way to define continuity at an interval, but it talks about limits and continuity at a point. So we do have some theorems similar to what we were talking about before with in class about if you add two functions that are continuous, then the sum of the functions are also going to be continuous. So this is kind of summarized in theorem 1.3, continuity of sums, products of functions. So suppose you have two continuous functions on an interval, and then you have a constant number. Then that means the scalar multiplication of b and f of x is also continuous. And then the sum of f of x and g of x on that interval is continuous. And the product of f of x and g of x on that interval is continuous, as well as the quotient, in other words, dividing f of x and g of x is also continuous, provided that g of x is not equal to 0 at all on that interval. And that is an important thing to note. And then the last thing is the continuity of composite functions, which is if I take a function, two continuous functions that are continuous on a particular interval, and I take the composite of the functions, as long as it's defined on that interval, then the composite function is also continuous. So I know that was a lot of content, but it's very important. Some of it was summary, and I think you'll do well on the assessment. See you in class.